So now we understand what the code looks like. Let's see what happens when we synthesize this, right? Synthesis, very straightforward. I just click that button. It says starting C synthesis. You can see the messages scrolling over there. It turns out this is very fast, right? Okay. So you will notice also over here that in this header file, I have two lines over here, right? The data type, I have got one type def as float, which I have commented out right now. The other type def as AP fixed is what is active. Now, while you are experimenting with the different types of code, this is probably a good way of switching between the two, right? You have one type def in one place. By commenting out one line and uncommenting the other, you can easily change the type def. So, these kind of things are nothing to do with how you write, how you design hardware. It is more a question of these are tricks to make your use of the tool a little bit easier. In this case, I am working with the AP fixed data type. Okay. So, let us see what happened to the synthesis result. Let us try and understand that a little bit. You can see over here that there is something called the AP underscore clock, right, that is mentioned over here. The target frequency that we had given, this was given while we created the project, was 10 nanoseconds. Target time period was 10 nanoseconds, target frequency was 100 megahertz. Okay. Now, this uncertainty part of it, just ignore for now. This is just a sort of safety margin factor that Vivado HLS puts in. For now, we can just ignore it. It does not really affect our results in any way. The point is, if your estimated value is more than 8.75, that is 10 minus 1.25, it is basically going to flag a problem, saying that you might have a timing error, right. Now, why this 1.25? Because we put a safety margin of 12.5%. Okay. If you had put some other safety margin, it would have done it correspondingly, but you can just ignore the safety margin altogether and just change your target if you are really concerned about it. The other thing to keep in mind, Vivado HLS estimates of timing and area are usually very pessimistic. What I mean by very pessimistic is they can be off by 20% easily, right. In some cases I have seen up to 50% off, right. So, if it tells you that the estimated period is 10.78 nanoseconds, usually after synthesis, place and route and so on, you will be able to get below 10. Okay. Similarly, the utilization estimates, also the numbers that we see over here, which we will go over a little bit more detail, are usually pessimistic. So, the numbers that it reports are typically a 20% overestimate, and after synthesis, place and route and so on, you will find that those numbers decrease significantly. But before that, let us try and understand what are the rest of the data that we have over here. One thing we can see is there is this set of values called the latency and the interval. Okay. Hopefully, by now the concepts, what is latency, what is initiation interval, all of you at least have the basic idea, because we have looked at a few examples as we go through. The initiation interval is how often I can feed a new FFT, a new block of 32 inputs to the FFT code. Okay. And the latency is how long does it take that first block of 32 inputs to finish computation. Okay. So, to understand this, essentially we can look at it as I have the FFT block, right. So, this is I will call this FFT 0 to indicate that it is the 0th iteration of the block. This goes from time number 0 up to time number 511. The next instant can start immediately after that. That is what the interval being equal to 511 means, right, and the next block can start after that. And so on. Okay. So, over here the initiation interval is equal to the latency. Okay. So, if I had a situation which looked something like this, right, now the latency would be this value, whereas the initiation interval would be this value. Right. So, in general you can sort of clearly understand that the initiation interval will be less than or equal to the latency in general. Okay. The other thing is a latency equal to 1 essentially means just compute and on the next cycle it is ready, which means there are possibilities in certain situations you might see a latency of 0, and latency of 0 essentially means it has managed to convert your whatever code you wrote into a combinational circuit. It is available in the same clock cycle that you give the inputs. Okay. A latency of 511, right, and if we expand this out, we will see that it actually gives you a bit more detailed information, saying in which instance, or rather what was the latency or the functionality of different instances of the overall code. Okay. So, what does this mean? If you look at this instance, it says there is some group FFT0 which has a latency and an initiation interval of 81 clock cycles. Okay. The way to understand that is the overall FFT code takes 511 clock cycles, but in that there is one group or one block of computation which is called the FFT0 block, which you can imagine basically corresponds to the function FFT0 that we wrote, which takes 81 cycles. So, you can imagine that what will actually be happening is there will be 5 such blocks, right there, because if you look at the code there are 5 FFT0s inside it, right. And in addition to that, there is also something for the bit reversal. The way that we have written the code is the bit reversal happens in front. And how long does the bit reversal take? We can figure that also out. It in fact, it does not create a separate instance for that, right. So, this is one thing which can potentially be a little confusing in how Vivado HLS generates hardware. You will see that the FFT0 block over here was made into a separate module. So, you can actually go inside it, see what happened in the analysis of group underscore FFT and so on, but the bit reversal is not a separate module. It essentially uses something called function inlining over here. Okay. So, what that means is even though your code that you had written has bit reverse as a separate function, when the compiler looked at that function, it found that the operation inside it was so trivial, just one for loop, that it basically just put that for loop into the main code. Okay. Which means when you do the synthesis, it gives you a result corresponding to that. It considers the bit reversal as just one loop and not a separate module. I do not need to send a separate start signal, wait for a done signal, etc. from bit reversal. I will just run it as a loop. Okay. How does a loop run in hardware? The divider assignment was basically about that. It is a state machine. You will start off with an initialization state which basically sets up the variables, go into a operation state where some counter is incrementing and checking whether it has completed the loop. During that time some other computations are being performed, and once all of that is done and the comparison says okay, I have finished running this 32 times or whatever it is, get out of the loop. Okay. So, this takes 96 cycles. So, going back here essentially what we see is that this takes 96 cycles, these take 81 each, right. So, 96 plus 81 times 5 should ideally have been this 511. Obviously, it is not exactly equal, right. So, all that is telling you is even though the latency of a block by itself is 81 cycles, starting the next block, transferring the data over to it and having all of this, there are some additional overheads, 1 or 2 cycles involved in each of those cases. So, adding up the individual module latencies will not give you exactly the top level latency, but it will be very close. Okay. It should be. Go further into this. In fact, what I can do is I can go dive deeper into the FFT module, right, and here I clearly see that the latency and interval are just given as 81. So, this is corresponding to one block. The interesting thing is the estimated time for this block itself is that same 10.779. In other words, this FFT0 is your bottleneck. You probably knew that to start with anyway. Okay. There are no instances over here. Why? Because there are no further function calls. There is a, so the FFT0, if you look at the code, essentially just corresponds to this loop. Okay, there are no further function calls over here. If there were function calls, they might have shown up as submodules or they might have got inlined, but the loop is there. So the FFT underscore label 1 loop, you can see that it has an iteration latency of 5, it has a trip count of 16. What does a trip count mean? You can see that the code essentially says I is equal to 0 to n by 2, n is 32. Okay. So this for loop is going to run n by 2 times, in this case 16 times, that is the trip count of a loop. The latency of one individual run through that loop is 5 clock cycles, right. Therefore, what you end up with is the trip count 16 multiplied by the iteration latency 5 becomes the total module latency, which is 80 clock cycles. One additional clock cycle interval, initiation interval, basically to take into account the fact that there will be one state required for the initialization and signaling the done of the system.